So there's two more things that we need to know how to do before we can actually start with a login system. So the first thing we need to know is the proper handling and storage of password information. The number one rule of dealing with passwords is never store sensitive information in plain text. So don't have a table or a column or whatever in your database with the password stored. What you should do instead is only store something that you can use to verify the user's identity without being able to get their original credentials. So the way we do this, it seems impossible at first, but the way we do it is actually pretty clever. So what we're going to do is we're going to take the password and we're going to use it to derive a pseudo-random value. And this value is going to be constructed in such a way that there's no practical way of taking the value and returning the original password that was used to generate it. So it's going to involve some complicated bit scrambling. And basically, it's like if you put an egg in a bowl, you can fish out the yolk. But if you put an egg in a bowl and then whisk it up until it's completely scrambled, it's really hard to unscramble the egg afterwards. And that's kind of like what we're doing here, is we're scrambling the egg in a way that is impossible to recover the original egg yolk. So the generic name for this kind of function that can take a piece of plain text and generate something that looks pretty much like a random number is called a hash function. And the way we're going to use it, I'm going to just pop up my Python again. And there's a package called bcrypt that has some handy functions for doing this. So import bcrypt. And bcrypt, I'm picking that because it's been around for a while and it's pretty widely used. And it's cross-platform so that you can use it. For example, if you're working in Java, there's a bcrypt library. If you're working in PHP, there's something that's like bcrypt and compatible, and Python, obviously, and so on. So it's really easy to support the same code on different machines. And it's reasonably secure cryptographically. So there are some newer ones which might be slightly more safe, but in a provable way. I mean, but practically speaking, bcrypt is about as good as any of them are. So there's two main functions that we're going to want to use here. So actually three. So before I show you the first one, which is how you hash a password, I'm going to say something about salts. So you start with the idea that you're going to take a piece of text and you're going to run it through this one-way function, this hash function, that produces a value that cannot be used to retrieve the original password. But if you give it the same password twice, it will generate the same hash value twice. And so you can hash the original password they give you, store the hash value in a database, and then when they go to log in, you take the same password, you hash it again the same way. If you get back a hash that matches, the user's proven that they know the original password, and so you let them log in. So that works fine, and it's true that the only way of taking the hash value and reversing it is basically to brute force through all the possible password combinations. And then you can start with more likely ones first and try limiting the character sets in various ways to reduce the total amount of search. But basically, you're running through all the possible passwords, computing the hash for each one, and then checking, was this the right password? Was this the right password? And doing that literally billions of times. So it's pretty good, but there's two places where it falls down. So the first place it falls down is if the user picks a really weak password, for example, like 2 or 3 characters, then you can probably run into that pretty quickly if you start with all the 1 character combinations first, then all the 2 character combinations, then all the 3 character combinations 4 characters, and so on, you're going to run into it by the time you hit the 3-character combinations, and you're going to find the right password. So your brute force search will work fine. So, so you say, okay, well, I'm going to require the user to type something sufficiently strong, like minimum of 8 characters and at least 1 uppercase, 1 lowercase, 1 digit, 1 special character, and so on, in ways to increase the chances that you have to do a lot of work before you find the right password. So that works pretty well, except that you might not have enough time to brute force through a large number of passwords, but what you can do is pre-compute a whole bunch of hash values for all of the different possible character combinations and store them in a database ahead of time. So people have literally spent weeks, months, years of compute time in order to generate hash values for all of the possible, or a large set of possible password values, and stored them in databases using a variety of popular hash functions. And then if you have already pre-computed the hash value for a particular password, even if it's a relatively strong password, then all you need to do is, if you get the hash value, you can look it up in the database. And if it's in there already, you know what the original password was. So this kind of approach, where you pre-compute the hash values for a large number of text passwords, is called a rainbow table attack. So the database table where you store those pre-computed hash values is called a rainbow table. And there are some pretty big rainbow tables on the internet that you can just download if you're interested in doing it. So how do you defend against a rainbow table attack? If you're already requiring reasonably strong passwords, what do you do to avoid those pre-computed rainbow tables? Well, the answer is you add something called a salt. So a salt is a big random value that you concatenate with the original password before you hash it. And while it's true that a rainbow table might have the hash value for the original password, it will most definitely will not have the hash value for the random salt plus the password. Because computing all of the possible passwords times all of the possible salt values, where a salt value could be like 32 bits long or 256 bits long, is definitely beyond any compute available. So that's the state of the art, is first you generate a random salt value, and then you use that in order to hash the password. And that's also a defense against rainbow tables. And if you require a sufficiently strong password, you have something that's immune to brute force attack and also immune to rainbow table attack. So bcrypt supports this by having essentially 3 functions that you are going to need to use. So the first one is something called gensalt, and you say bcrypt.gensalt. And if you don't give it any arguments, it just uses some defaults to generate this binary string, and it's got $2b, which is actually the type of hash, and then $12, which is something called a work factor, or number of rounds. Basically, it's a number that goes up exponentially, so 13 is about twice as hard as 12, and 14 is about twice as hard as 13, give or take. And basically, you want hash functions to be relatively slow. Not so slow that it's annoying to a user when they're trying to log in, but slow enough that somebody can't generate 1 billion hashes a minute. So with a number of 12 on my machine, it takes about a half a second to come up with one hash value. So running through hundreds of passwords takes a noticeable amount of time, and running through billions of them is just completely off the table. And then the actual hash value is a pseudo-random string of digits that have been converted into text-like string. So this whole thing together is basically a random value. And then I can use that to generate a password hash like so. So there's a pcrypt dot hash pw, and it takes a password. So like test me, it's not a particularly good password at all. But bcrypt is going to expect a binary blob of data. And this is a string. So what's the difference between a string and a binary thing that looks like a string except it has a B here? The difference basically is that you can take this binary string of data and it will always be the same values. But a string additionally has a character set. So underneath this string, there's binary data, but that binary data is interpreted based on a character set. And on Windows, it's most usually either Unicode wide, which is 16 bits per character, or UTF-8, which is 8 bits per character, but then some of them are multi-byte, or Latin 1, which is a character set where there's basically 8 bits per character, but it only has European characters in it. And then there are some other character sets that aren't used very often in this country. There are a number of different Japanese character sets and some Chinese character sets and so on. But mostly you're going to see Unicode in either Unicode wide or UTF-8 or Latin 1. So bcrypt doesn't know anything about that. It just wants binary data, but it's really simple to take a piece of text and convert it into binary. You just call the encode method of strings on it, and that returns a blob of binary data instead of a string. And then you give it the salt value. Now, I actually want to store this salt somewhere, but I'm going to generate a new one, bcrypt.gensalt. And I get back a bigger blob. Now, what isn't obvious from this particular example, because I didn't store the salt, is that this part of the hash value is actually the salt value. So the salt value is physically part of the returned hash so that I can use it later on in order to rehash the same password with the same salt to get the same total hash. So let's see what that looks like. So I'm going to repeat this gen salt, and I'm going to use 13 this time instead of 12, so it'll take twice as long. And then salt is equal to that. So here's my salt. And then I'm going to rehash the password, and I'm going to use the salt that I just calculated. And you'll see that the salt value matches the first part of the hash. And then this value is constructed in such a way that if I alter any one bit in the original password, roughly half of these bits are going to change. And you can't really tell which ones ahead of time. So it's basically like you take a random number, you generate a new random number based on that. And the less able you are to predict what is going to actually change when you change any particular bit here, the better the hash function is. So this gives me a hash, and let me do that again. So I'm going to go ahead and hash the same password using the same salt. And if I look at hash now, you'll see I get the same value back. So same password, same salt, same hash. But if I change this password, even like I change this E to an F, so that's probably 1 bit more or less, this hash looks completely different. So the salt is the same, but everything beyond that is completely different just because I changed that 1 bit. So that's how you know it's working. So I have the hash. How do I check to see whether I have the original password or not? So let's go ahead and regenerate the original password. Same value as I had up here. Now there's a check PW function. So bcrypt.checkPW. And I give it a password like so. in binary format, and I give it a hash. And it returns true if this thing hashed with the same salt that this thing has results in the same hash that this thing has. Now, if even a bit is different, I get back false because the password, when rehashed with the same salt, does not produce the same result. So that's how you can tell whether a password matches a hash value or not, while only storing the hash value in your database. And as I said, there's no obvious way that you could take this hash value and find the password that matches it other than brute forcing through all the possible passwords.